Okay, so problem set 3, right? This is our second problem set on chapter 2. It's just these two problems, but if you glance at the solutions, it's going to take us the whole time. Not that that's saying much with me. Let's see. So there'll be a... God, I didn't even look. There should be a quiz after this. Yeah, it'll be the second quiz on this chapter. Yeah, I'm pretty sure there's got to be one. Okay, so I'll send that out. No experiment this week. It's next week, all right? Okay, so the first problem here has to do with usually called a geophone. And it's used to pick up seismic vibrations, okay, like the Earth. And I should, I don't think I've mentioned something here, but I should have mentioned it the first day of class. Often devices like this are now available in MEMS, micro electromechanical systems, right? So I'm almost certain that I would bet money that you can get a MEMS geophone. I don't know. I don't really know. But you can get MEMS accelerometers. They have been available, they were available last decade. I remember talking about that in a 3000 level mechanics course I had heard from a professor here about a MEMS. And I got the product data sheet. It was kind of interesting. And also interesting is the fact that it operated very much like a normal size, something like this. So if this is available in a MEMS, it could be actually very similar to this, okay? So you want to be aware of this. MEMS have been around actually for decades, but they really started to take off in the 2000s. Okay. Okay, where were we? Right, so the idea here is this. This is called, they call this the or Brian calls it the foundation. I don't know, I mean, he's probably not the only one. And you attach this to something whose vibration you want to measure. So you can attach it vertically, if you can imagine rotating this 90 degrees. You attach the foundation here, or horizontally. And the idea here is that if this is moving because it's connected to something that has some seismic vibration or whatever, some vibration. There can be a relative motion. This is rigid right here. A relative motion between the magnet and the coil. And so this is very much like an electrodynamic microphone. It's a conventional loudspeaker in reverse, operating as a microphone that I demonstrated for you. There's a difference here in that usually we think of the magnet as being fixed, but here it's actually moving. Okay. And often an additional mass is attached here, and you'll see why. I only briefly comment, but you'll see why, and then you want to be able to adjust this mass. There's an important reason for that, having to do with the flatness of this transducer. Okay, so that's the idea. Again, you have a conductor moving in a magnetic field. There can be a magnetic force on the charge carriers, and that gives you a voltage. So it's the basic fundamental magnetic force law operating here. We're going to use script L as the length. I usually like to stay away from capital L because we often use that for inductance. So the length of the coil here is L. It's in a assumed to be uniform magnetic field B. And remember, all these quantities are complex. We'll call this U the velocity of the foundation. The magnet can be moving, the velocity can be different. There are two velocities here. Okay. The coil's going to be moving at the velocity U minus V. No. The coil relative to the magnetic field is going to be moving at that's the important quantity here. The voltage generated is going to be proportional to the difference of these two velocities. If the two velocities are the same, you have no relative motion of the coil, you're not going to have any. You're not going to get any voltage. So it's going to depend upon the difference there. Now, a complete electrically equivalent circuit does not exist here because the impedance analogy doesn't, you have to go to the mobility analogy, right? Because we have this magnetic field and conductor. But it turns out it's not going to matter here. We can analyze this electrically. And the reason is we're going to operate this in an open circuit. It'll be an open circuit operation. The leads from here will be attached to something that has very high impedance. Usually some kind of preamplifier, or you could directly put it into an oscilloscope. All these things have very high input impedance. So the current I is equal to 0 here. And that greatly, and we'll see this again and again in the course, that greatly simplifies the situation. We don't have to worry about the current. So there's no magnetic force on the coil here because there's no current. Okay, there's no magnetic force. So we will see, you'll see as we go along how that simplifies things. So the voltage here, as I said, is just going to depend upon the difference, and it's proportional to the velocity of the coil relative to the magnetic field, as you know, when you have a conductor moving in a magnetic field. And that, the difference velocity, so it's going to be proportional to that, and it's going to be proportional to the length, and what's left is just the magnetic field. So this is the usual BLI or BLU thing, except here we have to deal carefully with the relative motion. You've seen this before, just a straight wire, for example, in a magnetic field. That's what we did. We just have to use the relative velocity here. Now, we're going to treat the velocity as we're going to treat the transducer as a velocity sensor, not a displacement sensor or an acceleration sensor. And somebody's already used the word there. Those are called accelerometers, right? I guess you could call this a velocimeter. That word is usually used in fluid dynamics, but I haven't seen it here. But anyway, you may wonder, why a velocity sensor? Why? I mean, it picks up on displacement, it picks up on acceleration. It picks, once it picks up on one, you've picked up on all three. Well, there's a very good and important reason why it's considered to be a velocity sensor, and you have to wait towards the end to see why. Okay, and this is fundamental for transduction. And you'll see that, and I'll emphasize it. But thinking of this as a velocity sensor, then the open circuit sensitivity, this is in lowercase o here, it's not a 0, this stands for open. The open circuit sensitivity will be the volts per velocity, voltage per velocity. So it's volts per meter per second, okay? That's going to characterize our transducer. We would want to know that if we want to use this thing. We want to convert the electrical signal into what we want to measure, mechanical signal, vibrations. So now these are in general complex quantities. In general, there's a phase difference between the voltage and the velocity. Almost always you don't care about that. We just want to know the sensitivity. We want to know just the magnitude. You don't care about the phase. Now Brian has a tendency to not do this. So if you look at the answer in the back of the book, you'll see a phase. He actually solves for the phase between these two. But our policy is going to be just to ignore, we don't really care about that, so we're going to take the magnitude. Okay, so this is what we want to determine. This is the relevant quantity for the sensor. And pretty much for all sensors, I would think, right, is the sensitivity. That's sort of the bottom line for a sensor. And of course, buried in here is the fact that this may not be constant, okay? Or in general, what we're going to find is any reasonable transducer, most reasonable transducers, it's going to be constant, but only over some range. And that range is important because that's where you want to operate. It's so much easier, so convenient to have a sensitivity that's independent of frequency. It's flat, okay? Okay, so again, there's no magnetic force here. We don't have to, it's an open circuit. We really only have to treat this mechanically. It's a mechanical system. We've got to find we've got to find this quantity. Now I want to point something out to you. It's not in the solutions here. If you, suppose you're controlling U. From our general theory point of view, there's a force here that's causing this U. But it doesn't matter, just think that there's a U there. Suppose you, and you're at some frequency and it's in its steady state. Suppose you double U, what's going to happen? Take a wild guess. What's going to happen to V? It's going to double. Yeah, it's going to double. This is going to be linear. As long as this remains linear. If these coils, if normal operation, they're well inside the magnetic field, and they start to see the ends here, becomes nonlinear. Okay, then you'll have amplitude, you'll have a sensitivity that is amplitude dependent. Very inconvenient, right? So there's that amplitude limitation. We discussed that briefly the first week. So here you can see it here. Incidentally, I should tell you, there's another way of doing this. Typically, often, it's easier to have a longer voice coil. You just want to keep these two ends away from each other to avoid end effects. So you can make the voice coil substantially bigger than the magnetic gap. That's another way of doing it. So you just want, for this range of operation here, you want to avoid those end effects, because then that's when the amplitude dependence can come in. So we need to solve for this quantity, and it's going to, this U will scale. It looks kind of complicated here, but I want to point out that when by solving for it, you know, we're going to find that it's independent of U because we have a linear transducer. So here is we have two velocities. So, we could do this from a Newtonian analysis. It's certainly possible, but it's almost always substantially easier to use an equivalent electric circuit. So we're going to use an electrical circuit that's equivalent to the mechanical system here. We've got two velocities, so we've got to have two loops. And what's the relationship between the velocities here? They're the same. Whatever, technically the velocity across here is going to be the same as the velocity across there. The currents have to be the same. All right, and this inductor will just have this current V, right? So that really, it's unique. At that point, it's got to be this. No choice. We've got to have V going through the inductor. The current going through the capacitor and the resistor has to be the difference of the two. If the two are the same, you can see that there's no, from the mechanical system, the spring and the dashpot aren't doing anything. So this has got to be it, without a doubt. You can check it if you want to, but there's really no other possibility here that meets our requirements here. So this is very simple in this case. So we can, instead of solving Newton's laws, we just use the Kirchhoff's approach here with impedance. So if we view the circuit as a whole, then we think of this as a voltage, of course. This source here is seeing an equivalent impedance here, the mechanical impedance, which is just a capacitor. Okay, so there's the impedance. I add these, the equivalent impedance here is just the sum of the two. And the equivalent impedance across here is going to add in reciprocal. So 1 over the equivalent impedance here, that's Zm, is going to be 1 over this impedance plus 1 over that impedance, which is just the sum. So you get that, and you have to remember here that that's 1 over the input impedance. So you got to take 1 over that. Often you can forget this. That's there, right? We can simplify this a little bit, multiply through, and we get that. Okay. Now we got to get rid of the force. The force is irrelevant for our problem here, and that's easily done. You can see that there's the same voltage here, or force, across this combination. So we can write down the impedance, use impedance for that situation. The voltage across here has to be this impedance times this current right here. So we get this, easy. And now we just take the ratio. We can eliminate F here. You can just take the ratio of these two. And can you see what's going to happen here? We're going to get, if we take this divided by that, you're going to take this and put it underneath here with the left and the right sides corresponding. What do we get on the right side? U minus V over U, right? Which is what we want. Is that what we want? Or we want the reciprocal? Yeah, that's just what we want. So this is the quantity that we need to get the sensitivity, U minus V over U. And it's equal to this. Okay, with the mechanical impedance. And yeah, and there's a simplification here. It's interesting. There's simplification here, a lot of simplification. And I missed that when I was looking at this. Even when I stared at it, there's quite a simplification. That sometimes happens. That's usually a sign that there's an easier way to do the problem. But you know, this impedance approach is so standard, and it's so typically simple. You're less likely to make a mistake. Most people just go through that. They don't look for shortcuts. You know, they look for shortcuts using the impedance method, but it's just a standard thing to do, and you're much less likely to make a mistake. So the open circuit sensitivity, here we are. We just take BL times the modulus of this. So I need to clear out this denominator here. I'm going to multiply. Oh, that's easy. So you know that the modulus of this, do you see the right triangle here, the real and the imaginary part? Is going to be the some square root of the sum of the squares. It's very simple. We get that. And now, this is not such a simple expression, so it's a good thing here to essentially go to dimensionless units to deal with ratios of quantities. It becomes physically more transparent and easier to deal with when you do that. So I'll let you do this if you're interested. I checked it last night because I was suspicious that there was a mistake, but it's right. By going to dimensionless variables, by utilizing the mechanical resonance frequency, using that quantity right there, that parameter, right, and then going to dimensionless units like omega divided by omega naught, and using a dimensionless damping factor here, this turns out to be dimensionless, you can recast this into this form. Now, it takes up more space. Okay, you might say, well, that's not simpler. It's taking up more space than that. But it is. If you just stare at it for a moment, you'll see that it is actually much simpler and allows us to actually sketch. Yeah, question?
When you take U minus V over U in the top of there, shouldn't that be flipped? I'm trying to follow along and I'm missing that.
Okay, so are you questioning, we want, this is right. This is right.
Yes.
Yeah. Okay. So your question, oh, this should be flipped perhaps?
Yeah, that's...
Ooh. Yeah, maybe. It's possible. I'm trying to think because I know that the behavior. Okay, yeah, I see what you're saying. Let me look at this. So we got U minus V. Yeah, let me check that. I'll check that. So, yeah, let's not spend time on it right now, but I'll check it, and if it's, I'll send out a message.
Oh, no, you know what? I'm sorry. It's correct.
Yeah, I can see that it's a little complicated, and it's easy to get it flipped when you. That's why I didn't want to. It's easy when you take this ratio. You got to move the ZM. Is there a consensus here, or should I? I'll check it. I'm going to check it.
I no longer have a conflict with it. So.
Okay. Yeah, I think it's probably right, because it would screw up the
end result.
Yeah, which I'm pretty sure is right. Okay. That's not the best way to look at things. You shouldn't look at things that way. But you know, we all do, right? We're human.
Sorry about that.
No problem. Okay, so what does this look like? Now, your generation, I guess you put it on a computer. My generation, we didn't have computers when we were young, so we just stare at this and we look at limiting cases, right? And it really is a useful thing to do. And you can become actually very quick at it. So the one thing we might want to do here is look at small frequency. What do we mean by small frequency? What sets the frequency scale here? Omega naught. Omega naught is clearly going to play a role here, a fundamental role. So by small frequency, I would mean omega much less than omega naught. When omega is much less than omega naught, I kill this, I just get 1. I'm going to get a parabola. Do you see that? M is going to be proportional to omega squared. So down here, this is just a sketch. You can probably tell. Okay. That's part of a parabola. So my generation, we draw that. Okay. And then we go to the other limit over here, high frequency. And again, by high frequency, what we mean is much greater than omega naught. So now I can neglect the 1 here. And this is a higher power, so this is going to dominate. When omega is substantially greater than omega naught, it's going to dominate this. Okay, no matter what the dimensionless resistance is, eventually at high frequency, you're going to be able to neglect this. And then you get this, do you see what you get here? You get the square root of this to the 4th power. You get the same up there. So this approaches 1. And incidentally, if you want to be careful, it approaches, you can show that it approaches 1 from above. So the next thing we draw is this asymptotic behavior here. So we have the asymptotic low frequency behavior here. And then we recognize that we're going to we have a resonance. It's going to resonate, right? So the maximum amplitude is going to correspond to approximately omega equals omega naught. Remember 3119? If the quality factor is big, then the resonant frequency here will be, in general, and I haven't confirmed this in this case, yeah, this is going to shift the maximum. Okay, so I would say I'm certain here that the absolute maximum here is not going to occur exactly at omega naught, but it's typically close. Okay? So once you realize that, you can draw this. Now, I don't mention it in here, but I need to tell you one of the reasons transducers aren't usually cheap, okay, particularly measurement transducers, accurate measurement transducers, is they've gone a long way to make this device useful. So, before I talk about that, I need to say something here. So you can see here that out in this region, as long as you're sufficiently far from the resonant frequency, you have a flat transducer. But I want to point out that it's flat because we chose velocity. The sensitivity here is referred or corresponds to the velocity. It's the volts per meter per second, right? And if you're interested, and I went through this, you might say, well, I want to think of this as an accelerometer. So you can find the sensitivity. Now that we've solved this, it's an easy matter. It's a matter of factors of omega to find the sensitivity referred to acceleration, the volts per meter per second squared. You're going to find there's no flat region. And also as a displacement meter, you'll find that there's no flat region. All right? So this is why we call it, because we want to operate. This is the operating regime over here. Very convenient to have a sensitivity that's constant. So, getting back to what I was going to say earlier, you want to a manufacturer wants to make this as big as possible, okay? Or if you're having to build one from scratch, well, that means you usually have a specific thing in mind, but you may have a problem here. You may be interested in frequencies down here. What are you going to do?
Make a bigger mass.
That's one way of doing it. That's right. That's a standard way of doing it. Make a bigger mass. There's something else you can do that probably maybe not obvious to you guys, but it's very common in transduction, particularly acoustics transduction. I see it all the time. I look on charts for transducers. You can adjust the damping here to bring this down, to make it flatter going into here. So you'll see that. And typically they'll give it a little bit of the best thing apparently is typically it'll rise just a little bit up here and then come back. You can see this in microphone sensitivity. charts that come with microphones. For, good microphones, right? Measurement microphones. Now, so the operating regime typically will be here. Now, of course, in your particular application, you may want to operate right here, but you're just going to have to be careful. You may want to operate on resonance. You may be building something you intentionally will operate on resonance for whatever reason. Maybe you want to just get the maximum response. Maybe you've got noise problems. You're just going to have to make sure you use, the appropriate sensitivity, right? But typical for broadband application, you're going to operate over here. And the sensitivity is what? Well, we decided this was 1 asymptotically for large omega, so the sensitivity is just B times L. So that's simple. And not surprisingly, you increase the magnetic field, you increase the sensitivity, you increase the number of turns, right? And this all goes into the design, right? You can have a very strong magnetic field, but it's going to be very heavy. And there's going to be a limitation there. And how many turns can you wrap around this? Well, there's a limitation there too. So this is a classic transducer. And you can see why. It's got these important elements here of where the flat operating regime is and why we call it a velocity sensor and not an accelerometer or a displacement meter. Now when this is commercially, when you buy something like this, there's going to be a box, and you might be able to have a button there that you can push to make it operate as an accelerometer. But what are they doing? They're at the heart of the measurement there, inside the black box. What's actually going on in the transducer is the way we're treating, it's being thought of as a velocity sensor because we can use this flat sensitivity here. And it's just converting using a factor of omega to displacement or acceleration. So don't be fooled there. At the heart of it, this is a velocity sensor. And different transducers are different, there can be some that are inherently accelerometers. Maybe that's the right word to use here, is inherent. This is inherently a velocity transducer. Okay, so I think that's it for this. Great, a really good example of a transducer. So it's worth thinking about this, staring at it, because it's got a lot of common features to it, transducers, and it's fairly easy to understand. Anybody have any questions? And always, if you disagree with anything I said here, I did this some years ago. I remember being very happy that there was no flat regime for, it's kind of reasonable here, but it takes a little bit of a thought, but if you it's just going to be a factor of I omega going around here. You can convert this. Once we've got the solution here for velocity, you can convert it to displacement or acceleration. And I think you should find, according to the statement here, is that it's not flat anywhere. Well, unless you consider that to be flat, but that's pretty limited, right? Okay. Okay, now, I think there's just 2 problems in this chapter, right? So, we're going to do this one. And the reason I'm hesitating is this is one of the problematic problems. I think I mentioned to you this maybe the first week. Some of the problems in here, there's problems with them. And this is one, okay? So I had to decide, do I come up with another problem or go with it? I decided to go with it. I was able to get around the problem. And it is actually kind of interesting, as you'll see. So that's just a warning here. Here's the problem. Brian makes it sound like it's it's modeling a real transducer. He uses, I've forgotten, some kind of magnetic projector. He says something in there. I don't know if it's a realistic model or not. And you'll see in a moment why I'm saying that, because this is problematic. But here it is. This is the electrical side. Here's the mechanical side. We'll go ahead and think of this as the load. Okay. for later on in the problem. And you can see that the typical elements here are not in series as they usually are, they're in parallel. So that may or may not be unphysical. I don't know, but it causes it causes problems. That's what's causing the problem here. So this is going to require a different way of thinking than we're accustomed to. And whether or not this is realistic, I don't know. He makes it sound like it is, but that doesn't mean that it is. Okay, so first part is there's no problem in the first problem here. Part A. We want to look at the motional side and look at the the motional impedance. So the equivalent impedance here, because I have resistors in parallel, they're going to add in reciprocal. So here you see it. I'm adding the reciprocals, and then I'm taking the reciprocal of that to get that. So we're all familiar with that. We just saw it, in fact, similar. And now this is a numerical problem. So everything's going to be in SI units here. And we'll get back to this in a later part, the total input electrical impedance. Right now we're just focusing on the mechanical, or the motional impedance, okay? So this is the electrical impedance equivalent to the mechanical impedance. So it's got a capital M there. So we use all the electrical quantities here. Here they are. And I plug the numbers in, and it's complex, and we want to look at the real and imaginary parts. We're going to be looking in the complex impedance plane. So it's the real part versus the imaginary part. The resistance versus the reactance as you crank through as you change frequency, slowly change frequency. It's all steady state here, right? I think this whole class is, almost all of it is steady state. So I want to identify the real and imaginary parts. You see I've cleared the denominator here. I've gotten rid of this I by multiplying by the complex conjugate of this. So we get this. And now you can see the real part go away. Go away. Okay, so what does that mean? I got the cursor. Okay, so look at this. What's that? The real part. The imaginary part is this. There's a minus sign there. The imaginary part is that. So our resistance is here. I just was demarked there. Here's the reactance. Okay. Now, this is we're being kind of realistic here. We want to deal with frequency in hertz. So all these omegas here, it's going to be 2 pi times the frequency. Okay, 2 pi times f. So I graphed it here from, and you can do whatever you feel like here, whatever you want to do. You can explore this graphically. Please be my guest, right? Just whatever you have time and interest for, okay? So I did it from 1 to 5 kilohertz. And so here's what it is. And it looks a lot like a circle. You'll notice I have the same, it's a same scale here as I have here, I think, right? This is in ohms. It's stated in the text. I failed to put it in here. So this is 2 ohms here, that's 2 ohms there. You can see it's the same distance. And that looks like a pretty good circle. All right? In fact, I put these dots in, and that dot should be moved over a little bit. I don't know if you guys can see it. It should be moved over a little bit that way. Like this. This one's not bad. That's misleading, okay? Analytically, it's very easy to look at our 2 expressions, and you'll find, and you should do this, as the frequency goes to 0, you'll find that a curve here goes to the origin, and similarly at infinity. So that's very suspicious. It's suspicious that this is probably an exact circle, but I haven't confirmed that. So if you're interested, right? We don't have that problem that we had. Remember in lecture we talked about how you can have in frequency things can look something like this. And I know I laid some heavy math on you there, some advanced math, but because this is an infinitely smooth differentiable function, all right, this cannot be a circle. I know you're thinking, oh, you can certainly imagine putting a straight line and then putting an exact circle next to it, right? But if you think of this as one function here, you'll find that you have a discontinuity in some derivative here. It can't happen. So this cannot be an exact. I know that, but that is involved. Some higher math is involved with analytic function theory. Okay. But here we don't have that. We don't have these two straight parts, right? It starts here and ends there at the origin. So it's very suspicious. So you can either, now the reason I'm saying this is I'm hoping that somebody, I don't want to do it, okay? But if you get interested, you can try to do it analytically. That might be, I don't know, it might be messy, it might not be. Or you can do it graphically. You can actually look. You can take this complex number and subtract off this number. Does this sound familiar? We did this in a problem set. And do a spreadsheet analysis of that as a function of frequency and see if it's approximately constant. So you can do it. And nowadays, that's considered a proof. I'm okay with that. Okay. We don't have to do an analytical proof. Okay. So the motional resonance frequency corresponds to vanishing inductance, vanishing motional, reactance. X equals 0. So the motional resonance frequency, and you can, yeah. So we can get this from here. It's going to be the usual resonance, right? This being 0, this is like the usual series circuit. So that frequency corresponds to 356 hertz, and that corresponds 0 reactance. It's right here. Okay. Now we start to hit the. Anybody have any questions so far? Right. So far everything's been okay, I think. Okay. Now we got a little bit of a problem. Resonance. This is maximum impedance. The impedance is the modulus. Is the distance from the origin to the point on here. That's the modulus of the impedance. It's a maximum there. So it looks like that's going to give you minimum response. Maximum impedance. It should be anti-resonance. You would think this would be an anti-resonance. Okay. So that's the problem. And it's arising because we have a parallel circuit rather than the usual series circuit. So here's what's going on. You got to go back to the circuit here. And forget this right now. Just we're looking at the motional side. And imagine you put a constant voltage across here and you sweep frequency from low frequency to high frequency. What's going to happen? What's the current? What's going to be the voltage and the current through the resistor here? It's constant, right? I've got a constant, I'm sweeping frequency with a constant voltage amplitude here. The voltage is a constant here, right? Okay, so this, we're not resonating at the load here. There's constant power in the load as a function of frequency. What's happening over here? Okay, well, what happens is, as you increase the frequency, things are happening. There's some of the currents going, you're getting some current across here, and you can easily calculate because it's the same voltage. When you hit the resonant frequency, what happens to this part of the circuit? Yeah, the current going this way is equal, at all times is equal and opposite to the current over here. They cancel. They cancel similarly as we discussed whenever that was. So on resonance here is all of the current goes through here. But when you're off resonance, there's always the same current going through here. The source has to work harder. It has to get more energy out. So because there's no current here on resonance, that's what we mean by resonance here. What we mean by resonance is the system's not resonating at the load here. We're getting, zero current here. So we're going to stick with this problem, okay? We're going to stick with the word resonance. But I just want to make sure you realize that this is not resonating. It's resonance just in the sense that we're not dumping any current in here. Well, I guess one way of looking at it is, the source here, like I sort of alluded to earlier, the source here is going to find delivers. No, that's not good. That looks like never mind, it looks like anti-resonance. So anyway, we're going to put up with this, okay? Something we have to put up with. And I don't think Brian realized this. I don't think he fully realized that. I have his solutions, his handwritten solutions, and I've studied them, and I think he missed this. He was already old when he did this. He was well into his 70s. Okay. Now that may not mean much to you now, but it just gets harder to do these things when you get older. You'll find that out. So this is part of the problem here. In fact, I confidentially, great, this is being videotaped. Jay actually took this course from Brian in the 80s, later 80s. Did I tell you guys about this? Yeah. So, and he said, yeah, Brian was having old age problems then. Okay, that's right when the book came out in the late 80s. He'd been working on it for a number of years. So still, I think it's a good book, okay? I think it's the best one for us. But we do have things we have to put up with, and you're seeing one right now, okay? So let's carry on with this. Now, normally, for a normal circuit, and this will look familiar to you, you've seen it, and you saw it in 3451 and probably 3119. We have some impedance here, okay, and the impedance is and we have some oscillating circuit, some oscillating system. The power is, of course, the average value of I squared R, and we can eliminate I through the impedance here, and we get this expression. This is an expression that was important. It came up last quarter a number of times. I remember pointing it out to you. It looks complicated, but it just comes from two pieces here. It comes from the I squared R, the power, and using impedance here to get rid of the current. Because the current's a variable, usually the voltage is a constant. So this is that's the power. Now normally, resonance corresponds to zero reactance, and that's going to maximize this, isn't it? Because we're minimizing z squared. And to get the half power points, where do you go? Remember this from last quarter? This is actually really simple. The half power points, I want z squared to be doubled. I want to double z squared. So it turns out to be really simple here. The half power points correspond to the reactance being plus or minus the resistance. The reactance being plus or minus. That's going to give us, see, this is resonance when x equals plus or minus r, and we need both because there's just two half power points. That's why we need the plus or minus. When x squared is equal to r squared, we're going to double the impedance. It's going to give us another factor 2. The power has dropped by 2. So those are important points that we use to characterize a tuning curve or a resonance curve. So that's the typical case, okay? Well, our case is kind of the inverse of that. Okay. In our case, the motional impedance is constant. Yeah, the half power points do not exist here. It's constant power to the load, okay? But still, we're still going to call these points where normally you get half the power. We're going to call those the half. We're going to come up with those frequencies because they're characteristic frequencies for a system, okay? I'm going to keep calling them half power points for convenience, but they're not really. It's constant power to the load. You saw it. It's undeniable. It's constant power to the load here. We're just looking at the motional circuit right now. Okay. Now, we can still deal with these frequencies for which the reactance is plus or minus the resistance, the normal half power points. Except I want to point something out to you here. We've got a modulus here of z, right? Where is z going to be doubled? Well, nowhere. This is maximum z. For us, it's halving z. What's analogous to the normal doubling of the modulus, doubling the square in, you know what I was saying here, doubling the square. Let's see, where is this? Normally, we want to double the square here to get the half power points, right? And that occurs when x, compared to x equals 0, when x is equal to plus or minus r. Now it's flipped. Now we have it. The so-called half power points for us correspond to where this length is half the value. The square of this length is half the value. And that's going to be this length right here. Because this length, you know, this is the square root of 2 greater than this. And we have to double this. Any way you want to look at it, okay? This distance from here to here, the square of this distance, the square of this is twice the square of that. Okay, that comes from Pythagoras. So our half power points are these points right here. And it's due to this parallel connection rather than the typical series one. So I make a statement, here it is. Now, we want to determine these half power frequencies, right? One way to do it is, if you think analytically, you can go in here, set the reactance equal to plus or minus that, and solve. You get a quadratic equation, which is not surprising. Why is that not surprising? Why is it not surprising that we get a quadratic equation? Well, we got two solutions, right? F plus or minus. We got the two half power points. So, so I looked at that. I remember looking at this going, I don't want to solve that. So I did what you guys would probably do. I went to the spreadsheet, okay, for the graph, and just picked off these points here. This top point and this bottom point. I just looked at the spreadsheet. So this is actually accurate to 3 figures. Those frequencies are accurate. Okay, it's a simpler way to do it. All right. So we get these two, and we get those frequencies for the so-called half power frequencies. We can find the Q here, whatever meaning that has, is some kind of effective Q as the resonant frequency divided by the bandwidth here, and it's about 1. I don't think you're asked to do that, but now we're going to consider the whole. Any questions so far? Now it's going to get more complicated because we're going to consider the whole circuit. We're going to look at the total input electrical impedance across here. So we have to add that in. Now you go through a similar analysis. You take these functions here, and we need to add here, and you can see there's a real and imaginary impedances. So these are going to get, both X and R are going to change, but it's the same idea. And you plot it. Okay, it's the same idea. And now, look at this. So this is the total input impedance, the real part, the resistance, input reactance. And you can still see, we still have a loop here. Loops, as far as I know, always or almost always, in transducers, they denote a resonance, okay, when you see a loop like this. It's not at all like a circle. Now, part of that problem is I've expanded. I chose this scale. I just thought this was a nice scale to look at what's going on here. You can see that this scale has been expanded compared to that scale. So when you contract this to go to the same scale there, it will look more like a circle, but it's clearly not a circle. And it fundamentally, mathematically can't be a circle. And the second floor people up there would be happy. The mathematicians would be happy because of, can't have infinitely different, blah, blah, blah. Okay, so, and here are the half point frequency. That sort of helped me set the scale here, so I want to get those half frequencies on. And this actually goes down to 0 hertz here. So it's very different. You know, it can change things drastically with the electrical side. Now, second problem here, related to the first problem. Now, suppose we want to go to the so-called half-power frequencies. That corresponds to taking the square of this distance, and usually and doubling it, right? We don't have, oh no, sorry. So for our case, we've decided for the half-power points to take the square of this distance here, square of this impedance here, and to take half that, right? Do we get 2 frequencies? No, we're only getting, it's going to be right around here somewhere. We're only going to get 1. So that's a problem. So I decided we'll use the mechanical half-power frequencies, the supposed half-power frequencies, okay? The previous F plus and minus that we found. So that's the way around that. Okay, so now we're going to use that for the efficiency here. First of all, here's the general efficiency. It's the ratio of the power across the load to the power input. This is the current across the load. On mechanical resonance, what happens here? What's the current? The incoming current compared to the current through there? Please. It's the same, right? Because remember these cancel out on resonance? Okay, so that makes it very easy. Resonance is very easy. The currents cancel. They're going to be the same. And we just get this. The input resistance, well, I just see 2 resistors there, right? Resistance load, we get 55% efficiency. Now the so-called half-power points. All right, now it's not going to be as simple as this. Okay. However, at those so-called half-power frequencies, the motional impedance is given by this. Remember, the reactive part is plus or minus the resistive part. So if you have a current through here, the dissipated power, what's going to be important is this. You pick up a factor of 2 here because it's right in there, because this is half the load resistance. So this is the dissipated power. All right, so the efficiency is this divided by the total dissipated power, which is the power in the electrical side of the resistor, plus this right here. And now you solve this and you get 37.5%. So whatever it means, okay, whatever we've had to, this half-power points, we've just kind of cooked up here. But you will notice that the efficiency is less than on resonance. You'd expect that. Now, what the meaning of efficiency is here is I'm not really sure, okay, because we've had to play a lot of monkey with things to get this to work because it's problematic. But I think it's still useful to go through, okay? All right, and if you have any questions or comments about this, drop by my office or send me a message. Okay.